who has got up at the crack of dawn to give his presentation. Very impressed with that. For those that don't know Herman, he holds a PhD in geology from the University of Johannesburg. During his PhD thesis, he worked on regional correlations of sedimentary successions on the Kaapvaal craton using paleomagnetic analysis and zircon geochronology. Following the completion of his PhD in 2004, he spent a year working as a postdoctorate researcher at the University of Ottawa. In 2006, he joined Anglo Coal, where he first logged core and later worked as a geological modeler. In 2012, he joined Snowden, working mostly on reviews of coal projects for banks. From 2015 to 2018, he worked as a research associate at the University of Johannesburg, after which he started his own company developing software for geometallurgy. So Herman, over to you.
Hello everyone, thanks Aline for that introduction. Yeah, I think I'm really a field geologist in the sense that I like to look at field relationships. And if you're looking at field relationships, if you have a normal sedimentary succession, you expect that the oldest rock is at the bottom, an upright succession, the oldest rock is at the bottom and the youngest is at the top. Or if you have a dike intruding into a succession, the dike must be younger than the rocks that intrude. That is the relative geological relationships, and that's what I want to talk today about. But about these relationships, but then coupled to this, the isotope ages. So sometimes when we know that the rock, the oldest one is at the bottom, the youngest is at the top. But when we date the zircons in these rocks, we see that the older zircon is at the top and the younger zircons are at the bottom. So there's an inverted relationship, and this is a discrepancy between the field relationships and the isotope relationships. So today I want to talk about the discrepancies between geological field relationships and radiometric isotope ages. So this is the outline of the talk. I want to talk specifically about three things. First, about the theory of radioactivity that Rutherford and Gamow came up with in the 1900s. Then 7 types of these discrepancies that I've seen in nature and in observations. And then some further work that may be done in regards to this observations, to this discrepancies. So around 1905, Rutherford said that one can use radioactive decay, the parent and the daughter elements, the ratios of that to date rocks. And he said that his theory was that radioactive decay or alpha decay is a helium particle being ejected from the core of an atom, and with this at the same time a gamma ray is ejected. So that was Rutherford's understanding of radioactivity. So around 1928, George Gamow came up with an explanation in terms of quantum physics of radioactive decay. In normal Newtonian physics, the alpha particle would not be able to escape the core because of the strong nuclear force holding it. The nuclear force would be too strong to escape it. But because of the particle wave duality of particles, the wave function of the alpha particle exists outside of the influence of the strong nuclear force. So it's possible for the particle to be outside of the nuclei, and that's why radioactive decay takes place, is Gamow. Just something on half-life. This block represents all of the uranium-238 in the world, and then after 4.5 billion years, the half-life of the uranium-238, half of the uranium has gone to billion years, and has gone to late 206 and so forth. And this half-life is thought to be constant, and it is used in the calculation of ages of the crystallization of, for example, zircons. This is just the explanation of how we do age measurements. On the left, we have a picture showing the parent radioactive elements being incorporated, say, into a zircon crystal. The red are the 238 uranium, and the green is the 232 thorium. And then after 4.5 billion years, then half the uranium 238 has gone to lead 206. These blue spots, and because the half-life of 232 thorium is much longer, only have a little bit of has gone to 208 lead. And so then what you then do is you measure a spot and you calculate the ratios of parent and daughter elements in there, and then you come up with an age based on the half-life of the elements of the radioactive decay process. This is a sketch from my thesis that I've done that I completed in 2004. It's the cover sequences on the Kaapvaal craton of sedimentary rocks. You have at the bottom the Witwatersrand-Pongola supergroup, then the Ventersdorp supergroup, the Wolperg-Smitsdrift group, the Transvaal supergroup, the Waterberg group, and the Soutpansberg-Olifantshoek group. And at that stage, there was already quite a number of ages measured for radiometric ages measured for these successions. For example, there was in the Wits, Jens Gunsberg measured the porphyry sill at 2837 million years, and there was many tough units in the Transvaal supergroup and the lower Transvaal supergroup. For example, this Ridley's member 2470 to 2460, and then we have the Bushveld complex at 260 million years approximately, and then the Harty lava at 1928 million years. And this is what one would expect to see from the ages, that they decrease in age as you go upwards in the succession. This is what you, from the geological relationships, this is what you would expect. So just something on geology. This is the Drakensberg Mountains. You have the sandstones at the bottom and then the lavas at the top. And the sandstones are older than the lavas. This is the geological relationship that we expect to see in a normal upright succession of sedimentary volcanics. This is an outcrop from Greenland. It shows metamorphic rocks that's being intruded by two stages of sills. The light-colored sill dikes, the light-colored dike first, and then the black-colored sills dike secondly, intruding into the white-colored sill. So in this picture, the black-colored sill is the youngest rock, and the metamorphic rock is the oldest. This is from the Rutherford, two dikes intruding into the host rock. In this rock, the dikes must be younger than the host rock. This is from the Dwarsrivier outcrop. This is a chromatite xenolith in a northside intrusion. So the xenolith must crystallize before the rest of the intrusion and was incorporated into this intrusion. So it must be older than the intrusion of a northside. Now this is back to the Transvaal supergroup. It's been well dated over time, but the further we go, the more high resolution the dating becomes. So if you look at these ages, what I want to point out is the trital zircons that was dated in the Maghanieni diamictite. They have ages of about 2,220 million years by Bekes et al. In 2013. He published it in a conference paper, but there's been subsequent work on this, and I always find this T228 in the Maghanieni diamictite for the trital zircons. And then in 2016, Gamsted et al. Published a paper on the ongeluk volcanics. It's got a uranium-lead pedalite age of 24 million years, and also a sill intruding into the ongeluk lava. It's got an age of 2397 million years. So what we see here is that we know that the diamictite must be older than the volcanics, because the volcanics is on top. What we see from the isotope ages is the youngest tetrahedral zircons in the Magellanic formation is 200 million years younger than the overlying ongeluk volcanics. So there's an isotope discrepancy. Also, we see that this dike is much older than this. It's also about 150 million years older than the 2,220 million old tetrahedral zircons. And this is again a discrepancy because the dike must be younger than the rocket intrudes. It's an isotope discrepancy. So the geological relationship, we have the going upwards. The rocks get younger, and the youngest rock in this schematic illustration is the intrusion. It must be younger than the youngest rock it intrudes. But when we look at the isotope relationships in the diamictite, the dike, and the volcanics, we see that the diamictite is younger than the older volcanics, and the intrusion is older than the rocket intrudes. There's some interesting information. This uranium-lead information from shrimp was published it's in Gutzman and Beekes 1998. But what's interesting, this is the ongeluk lava. And there's zircons in there that's concordant zircons with ages between 200 and 800 million years. Concordancy is just agreement between isotope systems. So the 206-238 agrees with the 207-235 lead. So we see the young ages has got low uranium content. For example, this one has got 89 or 99 parts per million of uranium. So the possibility that these crystals were damaged by alpha decay, by the alpha particles being ejected from the atoms is low, because the uranium content is low. In fact, the zircons that are older in this set of data has got more uranium. So what we have is the ongeluk lava, and then we have pedalite and zircon. The pedalite has been dated to 420 million years, and we see the zircon that's around 200 to 800 million year old, concordant zircons. So there's more than 1,000 million years difference between the crystallization ages of the zircon and the pedalite in the lava. And this lava obviously crystallized almost instantaneously, so this mineral should be the same age, but there's a 1,000 million years difference. So it's a discrepancy. So, and also in Gutenberg and Beekes 1998, there's also many more of these examples of younger concordant zircons in tuffs lower down in the Transvaal supergroup. This is an example of shrimp data from my thesis in 2004. It was also published in Schroeder et al. 2016. But what's interesting here is I found a concordant zircon that's 5% discordant, and it's got an age of about 1,800 million years in the Magellanic formation. So if we then look at the Bushveld complex that intrudes into the Transvaal supergroup and into the Magellanic formation, it's got an age of around 2,060 to 2,055 million years, published ages. But this is much older than the rocket intrude, the 1,800 million year old concordant zircon in the Magellanic formation. So this is a typical example of an intrusive discrepancy in the isotope ages. This is from the Karoo supergroup. They've dated volcanism and dolerite with uranium, lead, zircon to about 182.5 million years. But Bowden 2013 has found detrital zircons in the sandstone below the lava for about 172 million years. So there's about 10 million years. These zircons are 10 million years younger than the lavas that overlies it. So there's a stratigraphic discrepancy in the Karoo supergroup that we know of. This is from the Soutpansberg formation, the Soutpansberg group. This is the Weilispoort quartzite being intruded by dolerite. The dolerite has been dated by rubidium strontium to 1769 million years, but that was an early date, and a later date by Hansen et al. In 2004 by uranium lead ambidaleite is about 1873 million years. But in my thesis work, I found by shrimp dating, I found the detrital zircon in there that's got an age of 1,391 million years. So it's about 400 million years younger than the dike that intrudes it. So there's an intrusive discrepancy in the Soutpansberg group with the dikes and the Weilispoort formation. Also, we find micro anomalies or micro discrepancies in zircon. When we look at the zircon grain with core and rim, we would expect that the core formed first and would be the oldest material, and then the rims would be consecutively younger. But I found zircons where the core is younger than the rim. So so we expect it's older, it's actually younger. This is from the Jack Hill zircons in Australia, as published by Kavosi et al. In 2004. Here we see an age in the core of 3950 million years. And then further out in the rims, we have an age of 3424. So there's about a 400 million years difference between the core and the rim, but the core is then isotopically younger. So this is a isotope discrepancy. This is from the Limpopo belt. Every zircon in this picture that has been analyzed twice has this anomaly, this discrepancy. For example, this zircon, it's got a core of 2938 million years, and if you look at the rim, it's got an age of 3231. So there's almost a 300 million years difference between with the core being younger than the rim isotopically. Just an anomaly example from Turkey. If you look at this zircon, it's got a core age of 2552 and a rim age of 2630. So it's 100 million years difference between the core and the rim, with the core being 100 million years younger. Just another type of discrepancy. When we look at lavas, we would expect that the same mineral crystallize almost instantaneously. So the single zircons that you find in these lavas should all have approximately the same age because they crystallize at the same moment. But I found, for example, the zircon is 1957. It's a concordant zircon, and then this one is about 2057. This number 8, the analysis. So there's a 100 million years difference in the age, but we know that it crystallized almost instantaneously at the same time. So it's the data, the shrimp data from that, and from this sample. The sample is about the size of a soccer ball. So this, for example, this zircon has an age of 1957, and this one has got an age of 2057. So there's if you look at the uranium lead ages, then there's a 1,500 million year difference between the youngest and the oldest zircon in there. But there's between the concordant lead ages, there's 102 million years difference between the youngest and the oldest zircon in rock that have crystallized almost instantaneously. Another type of discrepancy is where you have high uranium content in the zircons. You would expect with an old rocks, you would expect a lot of crystal damage to have occurred. But when we look at these rocks, for example, that all these points were dated, so we thought that they looked as if they were not damaged. Otherwise, we wouldn't have analyzed them in the spot. But there are zircons that have got more than 2,000 ppm uranium in these rocks, and they really don't look as if they have damaged that have been damaged. So this is another type of discrepancy where you would expect that the zircon was damaged, but it is not. This is from the Sealam formation of the Volkberg group. It's also from my thesis, the SRIM data. So we see a lot of discordant data with some concordant points in here, and this is discordant for the 206 lead 238 uranium, 207 lead 235 uranium. So in between these two mother-daughter ratios, there's a lot of discordancy or disagreement. However, I then looked at the 208 232 thorium, and for example, we had a zircon there with a 206 238 lead age, or 206 238 age of 953 million years. And it's only 10% discordant with the 208 232 thorium. So in another system, and if you compare two different systems, the one is concordant and the other is discordant. So what would you believe then? So if this age is already 953 million years, it would cause discrepancies with all the Transvaal supergroup, the Bushveld complex, the overlying red beds, and so forth. So today I've shown you 7 types of discrepancies. The first, in a normal sedimentary rock succession, where the oldest rock is at the bottom and the youngest rock is at the top. I've shown where you find isotope ages where there's older isotope ages at the bottom and at the top, and younger at the bottom. So there's discrepancies like that. We have found there's dolerite that have older ages than the youngest rock. It intrudes. We have zircons where there's more than, in a rapidly quenched rock where there's more than 100 million years difference between the oldest and youngest single zircon. We have looked at lavas with 2 different mineral systems, pedalite and zircons, where the crystallization ages are more than 1,500 million years different in rock that quenched almost instantaneously. I've shown metamorphic zircons where we know that the core is older than the rim geologically, where it's inverted isotopically, the rim is younger than the core. I've shown you zircons with high uranium contents, but with very little decay damage, where one would have expected a lot of decay damage. And I've shown you that there's dependent on the systems of parent daughter elements you're looking at, there might be discordancy or concordancy in the same analytical spot. So there's been many explanations for this type of problems in the uranium lead age dating. I list a few here. First is contamination. You contaminate you put zircons from other rocks into your samples. But we know that careful work has been done in this work, and even these, like the bedalites, were analyzed in situ in fin section. So it's very unlikely that it was contamination. People think that there's lead loss due to the radiation. However, in the ongeluk lava, I've shown low uranium zircons that have little damage, but they still have much lower than expected lead. I've shown xenocryst, or these pedalites, for example, in the ongeluk could have been xenocryst, but it's unlikely that now in the formation of pedalite that it would be xenocrystic. And this lead age of about 2,400 million years, the same as the pedalites, is very persistent in the dolomites above the ongeluk lava as well. So it's unlikely that it's xenocrystic. So in my opinion, these discrepancies is likely to be primary isotopic signatures. So some further observations that one can make in the discrepancies. We know that the alpha particles emitted by decay causes crystal damage. So we can go and look at young high uranium zircons in old rock that display very little radiation damage. We know that the high uranium will of course crystal damage, but by Raman spectroscopy we can look at the crystal quality and see if it's damaged or not. And if it's not damaged, then it would be, if you have high uranium and an old rock, then it would be a discrepancy. And we can also look, for example, for crystal damage in those in the metamorphic rocks where we have young cores and old ramps, to see if the young cores were damaged by radioactive decay, the emittance of alpha particles. So in conclusion, Rutherford, he used his method and he was satisfied that his method worked because those rocks that he first looked at, they showed this, the geological relationship was followed by the isotope relationship. But now with modern data at higher resolution, we find that the isotope ages doesn't always follow the pattern of the geology. And for this, perhaps we could incorporate a grading system such as we have for the paleomagnetic data. So they have tests like a conglomerate test or a fold test. We could have intrusion test or xenolith test to see how primary the isotope signatures really are. We can do further work on zircons, comparing concentrations of radioactive elements to crystal damage. And then I think we can engage physicists and chemists to explain this discrepancies. But I think there will always be explanations like contamination or lead loss or something like that. So you won't really, from data you gather from nature, we're not going to get any conclusions regarding this. So perhaps the only way to get to a conclusion would be to perform an experiment under controlled conditions. How such an experiment could look like is we could have, in a solution, we could put salt and radioactive element with a relatively short half-life. The crystal then grows and incorporates the radioactive element into the crystal structure. And we observe this with camera or video, so we know how far this crystal has grown and how fast it has grown. We then take the crystal, we know what the actual growth time was, say it was 1 week. We know that from the camera work. We then analyze pits in the crystal at different growth stages. So then we have the isotope time for the analysis, but we know what is the actual time it took, so we can compare the isotope ages to the actual age. WhatsApp audio. So for this, I have an hypothesis. It's that there's this fractionation existing that is not mass related to the atom mass. So so there might be fast and slow decaying uranium-238. So I call it decay-tope. So even though, then the fast decaying isotope gets incorporated into the crystals first. So it decays fast and then looks older, but it's actually not that much older than rock that might be above it. So that's my hypothesis. And thank you for listening.
Thank you very much, Herman. Nolene, do you want to take over from this point?
Happy for you to carry on, Craig.
Okay. Look, I'm sure there's lots of questions and comments because the conclusions are fairly radical. So I'll open up the floor to questions and comment. I'd like to start with just one query. Herman, what was the analytical technique for most of your experimental work, your dating work? Was it Sorry?
My work in my thesis, the experiment, the data was obtained by shrimp analysis in Canberra and in Perth on the zircons.
Okay.
For example, my work was by shrimp.
Okay. Was any of it done or tested using LAICP-MS?
No. The diamictite from the zircons from the diamictite that was dated by laser ablation, ICP-MS, and also other methods that the title zircons. I think it was dated more than 4 samples, and all these samples gave this young age of 220, and it was concordant. Some of those zircons are 100% concordant.
Yeah. All right, I'll open the floor up for questions and comments. You can raise your hand if you like, or you can just unmute your mic and fire away.
I see Johan Lawrence has unmuted himself.
It's very interesting, but I don't know if I can.
Johan, we can hardly hear you.
Let me try. Is this a little bit better?
That's a little better.
Yeah, my mic and my PC is not very well. I've got to get a different setup. No, I don't think it's very interesting to me, but I don't have any comments or suggestions to make.
Any other comments, questions, queries? Maybe just one comment from me. It's been a long time since I've been a geochronologist. But over the years, I mean, for those of you who don't do or have never done geochronology, it's a little bit of a black art still these days with the high precision analysis methods that you have. But I used to have a kind of a measure of robustness about a specific sample or a specific date. And you ask a hierarchy of questions. Firstly, can you repeat the result in the same lab using the same method? Can you repeat the result in the same lab using a different method? Can you repeat the result in different labs and by different methods, and so on and so forth, until you work up a degree of certainty on your age? And I think what Herman is suggesting here is that there is mass-dependent fractionation that we're not taking into account in some of our heavier isotopes, which is a fairly controversial conclusion. There have been papers written on it in the past 10 years. I must confess I haven't followed it very well. I don't know if anybody else has.
Craig, maybe just a comment. It just with that beduidelijkheid in the ongeluk, it's 200 million years older than the Magellanian diamictite zircons below it. So it seems as if it decayed faster. If you can see, the lead 206 formed faster than in the beduidelijkheids than it formed in the zircons below. So there's differences it would seem as if there's a difference in the half-lives. That's why I'm saying there might be mass-independent fractionation of
independent fractionation.
Uranium.
Any other comments or queries?
Yeah, I think I don't know if the spatial data that represent your result maybe we can resampling again as spatial and make sure about the is the data is represent or not for the spatial, just repeat it again, maybe. That's all.
Yeah, maybe just a comment on that. Like the Magaliesberg information, where we got that 1,800 million year old concordant zircon. There was just about 60 spots in that sample. So that one zircon represents more than 1% of the data. So if you would analyze if you would take more samples from the Magaliesberg, I think you would be certain to find more of those young concordant zircons. And the Magaliesberg, the Magaliesberg diamictite, there was more than 4 samples from different spatial areas that also, all of them gave that young T2 20 million year old age.
Any more comments or queries or questions?
Herman, Steve McCourt here. Have you had an opportunity to discuss your proposal with a couple of physicists? I mean,
I've talked to a physicist in the US who's they're looking at new physics, and they were looking at beta decay, but they also found many examples where the beta decay half-life wasn't constant. So I talked to that person a while ago. It was almost 2 years ago, but we haven't worked any further on it. But there's examples from beta decay that they think that's also not the constant half-life.
okay.
It was from Purdue.
Can I just ask, you've never had a sample where statistically the dates that you get disagree with the stratigraphic field relationships? I mean, you get these outliers which you've pointed out to us, and which you're obviously giving people a lot of food for thought, but you've never had a sample where the great majority of the ages that you get don't agree with the field relationships.
Statistically, I think the best example we have is that the medailleite in the ongeluk and the diamictite in the tetratyl zircons in the Magaliesberg. Because there was from more than 4 different areas, the Magaliesberg was dated by different methods in different labs. So, and all these samples gave the 2 to 20 million year old concordant ages. And the work done on the ongeluk lava seems to be very robust as well, that 2,400 million year old age by Gumsley et al. So I think that's the best example we have. But I would love to do more work in this and gather, like for the Magaliesberg formation, that would really be a different interpretation of the isotopes if you can show from different areas that you have this young 1,800 million year old age in the Magaliesberg formation of the Pretoria group. So then, yeah, but you have to do more work.
Mm-hmm. Yeah. Okay. Thanks.
Are there any other questions or comments before I close the proceedings? I don't see any hands up, and I don't see any mics unmuted.
Craig, I'd just like to thank Dennis Blewett and GeoExplore Store, who has sponsored all our talks for June.
Okay, thank you very much. And thank you, Herman, for doing this. I know it's pretty early in Colombia, so hopefully go back to bed and get some more sleep. Thanks to all our delegates for tuning in. We'll see you at the next lecture, which Nolene, I think is Friday.
Craig, it's actually tomorrow. We have Larry talking about...
Okay, I think we've lost Nolene. But with that, we've got Larry Meinhardt tomorrow at the same time, I believe. So thanks everybody for tuning in. And with that, I'll end the meeting. Thank you very much.
Thank you. Cheers.
Thanks.